Let's turn now from the past to the future. Although we understand now a great deal about what happened during the past 13.8 billion years, many mysteries remain. What was the ultimate origin? What's our ultimate fate? What is our universe really made of? The most popular theory for how things began, inflation, first we want to test with experiments whether that really took place. Then we would like to know what the detailed physics of it is and what, if anything, happened before that. If we look in the other direction towards the future, we're forced to face up to this question of what's going to happen, which is linked to what our universe is made of. And we're in this very embarrassing situation now that we still have no clue what 95% of our universe is made out of. We used to think it was all atoms, but now we know that our atoms make up only 5% of the cosmic matter budget. The remainder, the stuff we have no clue about, we've come up with two cutesy words for this, but these dark matter and dark energy are really just fancy words for our ignorance right now. So how is it going to end then? If we take our best theories of general relativity and so on and plug them in, there are 5 possible cosmochalypse scenarios for the distant future of our universe, which have been talked about to various degrees. The big chill, big crunch, big rip, big snap, and death bubbles. If we write down the equation at the bottom here, the Friedmann equation that governs the expansion rate of our universe, this h that we talked about before, which links the expansion rate of the velocity of something to how far away it is, right? For the simplest case of a flat universe, it says that this expansion rate is simply governed by g, which is the gravitational constant which we know, and the density, the total density of all the stuff in our universe. So it matters what the stuff is. If the stuff is such that the density always stays positive, this equation shows that the universe will always have a positive expansion rate. It'll keep expanding forever, giving us the big chill here on the left. If instead this dark energy, the dark horse in the race, can go negative, which it might, then it can bring the total density in this equation to 0. So h equals 0, the expansion stops, and eventually everything recollapses in a big crunch, making a black hole and a huge mess. If instead this dark energy sort of undilutes and gets higher and higher density and reaches infinite density at some finite time in the future, that'll cause the big rip, where everything, first galaxies, then stars, and eventually even the atoms that we're made of get ripped apart. If space itself turns out to not be infinitely stretchy, much like a rubber band is not infinitely stretchy because it's ultimately made of some sort of granular stuff, atoms, then, just like when you stretch a rubber band too much, when you stretch space too much, something bad might happen, the big snap. And finally, if it turns out that the dark energy is an unstable substance that can undergo some kind of radioactive decay or some other sort of decay, we could end up with these death bubbles. Just like if you have water, which is hypercooled to lower than 0 Celsius, but you haven't touched it, it's still liquid. All of a sudden, if you disturb it a little bit, you get a little bit of ice, you have an expanding bubble of ice that soon percolates and fills, freezes everything. We could have a death bubble like this where space itself freezes effectively and turns into a different kind of space that doesn't support life, which would be a bit of a bummer. That's the 5th scenario here. What's going to happen? First of all, I wouldn't lose too much sleep over this because most of these things are very unlikely based on the research we've done to happen anytime within the next billion years or so. We need to worry more about human self-inflicted disasters before then. But if you want to know what's going to happen, you notice that pretty much all of these scenarios hinged on what dark energy does. So interestingly, to know our destiny, we need to understand dark energy. Now, I'm a kind of impatient guy, so to figure out quickly what dark energy it was in time for meeting with you, I went to the source of all knowledge, of course, the Google image search, and discovered that dark energy is actually a bioblend nutrient additive. And if you read the fine print, it says It stinks, but it rocks. And this is true, because I actually ordered one on Amazon and I had to move it outside the house because it smelled so bad. But it also stinks, but it rocks really summarizes very nicely how I feel about dark energy. Because on one hand, it rocks, because if you just assume that there is this substance which is completely constant, it fits all our data beautifully. But it really stinks that we don't know what it is, and therefore can't predict our future properly. So the billion-dollar question in our quest to understand this better is it constant? Is it constant in space, like it seems to be, having exactly the same density everywhere, wherever we look? And is it also constant in time, in the sense that it doesn't dilute at all and just keeps its density the same? Well, there are fortunately a lot of different experiments going on right now trying to look more carefully at data to see if it is constant or not. And if anybody discovers any way in which the dark energy is not constant, either in space or in time, I'm pretty confident they're going to win a free trip to my hometown of Stockholm. And a particularly powerful way of learning about dark energy is to simply look at the billions of objects that adorn our universe, and for each one of these luminous objects, measure just two numbers. Measure how dimmed it is, and therefore learn its distance, and then measure how redshifted it is, and therefore know how fast it's flying away from each other. And then just plot the distance against the recession velocity like this to measure this expansion rate, this h, the Hubble parameter that we've kept talking about here. Since we can see these objects many different times in the past, we're therefore able to measure exactly how fast our universe was expanding at different stages in the cosmic history. And from that, we can infer exactly what the density of dark energy was at various times in the past to see if it was really constant. So let's turn now from dark energy, that big mystery, to another big mystery. What is dark matter? We have 4 roads to learn about dark matter. We can either catch it, make it, infer it, or weigh it. So far, the best evidence we have for dark matter comes from weighing it. That's how it was first discovered. Weighing things in astronomy is perfectly doable, even if you can't see the thing you're weighing. All you need to do is find something which is affected by its gravity. If you want to weigh the sun, just look at Earth, for example, and look at the orbital period of it around the sun, look at the distance, the radius of this circle, plug it in to the laws of gravity, it tells you how many kilograms of mass there is. Now, the shocker was that when Vera Rubin first did this to our galaxy and figured out how much mass is there actually in the galaxy in different parts of it, she found that there is much more stuff there than there is in the stars. That in fact, most of the kilograms in our galaxy are in an invisible form. You might want to think of dark matter really as being invisible matter. There's about, and there's in the ballpark of 5-6 times more dark matter in our universe than all the atoms combined. Another way you can weigh invisible matter, dark matter, is by exploiting the fact that gravity bends light, which was a prediction of general relativity. So if you take a photo of this cluster of galaxies here, light from other galaxies in the background have been so bent by the gravitational force of the dark matter that's here that some of them have gotten really warped out of shape. If you see these strange long arcs here, they're actually relatively round galaxies that have been so warped out of shape as your face might be if you go to an amusement park and look in one of these funny mirrors. And if you look more generally, a lot of galaxies here actually look more elongated and elliptical than they really are. So if you have a lot of dark matter around, things end up looking more oblong than they really are, and in a correlated fashion. So what we can do is we can look for these elongation correlations, these ellipticity correlation patterns, and infer from that how much dark matter there is in different places. A very spectacular example of that is this image here. So what you see, first of all, in the black and white part of it is just a regular photo with an optical telescope, which shows that there are 2 galaxy clusters. There's one here and another one there. They have actually collided with each other in the past and mostly missed each other and come out on the other side kind of unscathed. But the gas that was there between the galaxies couldn't interpenetrate it, made a huge traffic accident, which can be seen here in the pink, which is an X-ray photo overlaid. So the gas got kind of stuck here in the collision region as the galaxies continued out. And what about the blue? The blue is where the dark matter is, inferred from this gravitational lensing technique, the way in which the matter has bent light. And you can see that the dark matter didn't get stuck in the middle of the gas. It's moved along, interpenetrating all the other dark matter particles and coming happily out on the other side. So what this and all the other data we have on dark matter shows is that dark matter, whatever it is a very shy kind of substance. It doesn't like to interact much with atoms. So if a dark matter particle strikes my hand, it'll typically hit it, go through, hit the Earth, go through Earth, and out on the other side. Most of my colleagues think that dark matter is some kind of new particle, or maybe several kinds of new particles. But in our best physical models, even though they're very shy, kind of like the neutrino ghost particles that have already been detected, they do still sometimes, once in a blue moon, bounce off of an atom. And that's the idea behind trying to catch them in a laboratory. Many labs around the world have these fantastically sensitive detectors where they're trying to wait until a dark matter particle bounces off and they can detect it. And it's a very exciting time now. It's very competitive. And the experiments have finally gotten sensitive enough that it wouldn't be too surprising to me if you read on the front page of the New York Times in a year or in a few years, the big bold letters, the dark matter detected. Another thing we can try to do is to infer the presence of dark matter indirectly. For example, if you take photos of the middle of the Milky Way galaxy with a gamma ray camera, you see these crazy bubbles that are 50,000 light years from side to side. They're known as Fermi bubbles. And people are arguing passionately about what's causing them. But perhaps one of the most popular explanations is that they're actually caused by dark matter particles in the middle of the galaxy, where the dark matter density is the densest, bumping into each other and annihilating and producing gamma rays, which make these huge bubbles. This and other indirect evidence is a very exciting and active field right now to look forward to. And in addition to that, we can make dark matter, perhaps. In the Large Hadron Collider, when we smash particles together near the speed of light, a lot of this energy in the collision can be arranged according to E equals mc squared, perhaps into dark matter particles. Perhaps the lightest supersymmetric particle is a dark matter particle, for instance. And finally, last but not least, weighing it. That's how we first discovered it, and that's something we can do so much better by more accurately mapping out all the gravitational forces out there in the cosmos. So far, we've only used that technique to learn one number about the dark matter, its density. But I would love to see if we can measure more. Maybe we can measure if the dark matter has a temperature, some sort of viscosity, or any other properties that can give us a grip on what it is. To explore on this theme a little bit more, both to learn more about dark matter, also to learn more about dark energy, and about inflation and our cosmic future, it'll be wonderful to map out in more detail what the gravitational forces are, and in general, what's going on in our universe. So to end on an optimistic note, let's take a look at how little we've accomplished, how much information is out there still for us to harvest. Let's peel off the surface of this picture and see that these great microwave background baby photos of our universe actually come from only a tiny fraction, much less than 1% of the volume of our universe. And those grand 3D galaxy maps that we flew through also are mainly probing a tiny fraction of the volume. How can we map out the rest? There's more than 100 times more volume out there that we haven't really charted yet. It's much like when people first started exploring Australia, for example. They'd sailed around the coasts, but didn't know much about what was in the middle. We cannot, no matter how big telescopes we build, see galaxies out there, because there aren't any. Right? This is so far back in time that galaxies haven't had time to form yet. But everywhere in this volume, there is the hydrogen gas, out of which the galaxies later formed. And a wonderful fact about hydrogen gas is it gives off radio waves that are 21 centimeters long. So with a really good radio telescope, we can map out how much hydrogen there is in different directions. We can also figure out how far away these hydrogen signals are coming from. because these 21 centimeter waves get stretched with a stretching of space and get longer and longer. So if we get one that's detected to be 210 centimeters long, for example, we know that that came from so far away that our universe was 10 times smaller then. So with a really good radio telescope, we can make three-dimensional maps of our universe, which would blow away what we have so far in cosmology and overtake even the cosmic microwave background as the most sensitive cosmological probe, at least potentially. So there's a race going on now in the world to try to do exactly this. This goes by the geeky name of 21 centimeter cosmology. And we at MIT have had a lot of fun being part of this race, and I want to share with you just how much fun and how easy it is to build really state-of-the-art radio telescopes. You can actually do it in just 2 minutes if you move fast. This is one of the reasons it's so much fun for me to get to work at MIT, because there's so many awesome students. It's such a treat to be with. And what you saw here is the fundamental reason why this new generation of telescopes is so cheap to build is there are no moving parts. If you tell your friend that you need a 1 square kilometer radio telescope dish that has to be able to point with a big motor, that person won't be your friend anymore. And it's also it will be prohibitively expensive, right? However, here, all we do is we mass produce these cheap antennas, just measure the volts coming from the sky, and then we leverage off of the huge investment of the computer industry to just figure out what the sky must look like. And what's so cool about this is we don't just get an image from one part of the sky at a time. The computer can figure out what the whole sky looks like all at once. And moreover, by putting the antennas in a particularly clever pattern, we can make this design vastly cheaper than previous designs have been. We're so happy with how this technology demonstrator that we did worked out that we've teamed up now with a bunch of other universities across the US to put in a proposal to take these ideas and build something much bigger, which would cover about almost 0.1 square kilometers. You can see for reference, this is a pretty big thing here. And this would cost not billions of dollars, but 15 million for an experiment which would actually have the potential to be something which can ultimately overtake the best measurements we've done of any other sort in cosmology. So to summarize, we don't know the future of our universe, but we do know that the future of the study of our universe, the future of cosmology, is very exciting because we have plenty of wonderful mysteries to pursue, and we have a lot of really exciting experiments that are giving us fantastic new clues about these mysteries. So thank you.